Welcome back to our practical problem solving clinic, Understanding Variation to Solve Problems. This is part 2 of a 3-part series. This is part 2, identifying types and sources of variability. Well, Arnold looks like he's in an awful lot of stress in this picture, but you should be able to recall from part 1 that variability comes in 3 basic forms. First, normal variation from the mean, that's described by variance or the standard deviation. Instability of the mean or standard deviation, and mean off target. We'll be going through each one of these in detail. First, normal variation of the mean. So you see the bell-shaped curve there with the average about 74, and it has some variation around the mean, and that is described, and that's pretty normal for many processes. We know that all variables, process outputs, show some sort of normal variation and dispersion about the mean. And this dispersion is measured by the standard deviation or the variance of the distribution. That's the statistic that describes the width of the distribution, normal variation of the mean. Instability of the mean is when the mean changes over time or perhaps because of some other factor like a tooling change or a material change or someone actually changed the settings of the machine. So source 2A of instability is instability of the mean, a shift in the process. 2B is instability of the standard deviation. So in the previous slide, we talked about instability of the mean. In this slide, we're talking about instability of the standard deviation. So for example, here is in time 1, normal variation of the mean, and something happened in time 2 to create excess of variation around the mean. So what could cause something like this? What would cause the variability or the standard deviation to increase? Well, introduction of materials that has more variation inherent to it, or perhaps inaccurate or unreliable gauging, or perhaps many adjustments to the process, or different operators running the process at different settings. All of these things would contribute to increasing the variability about the mean. And when we see variability about the mean increase, that's a natural indication that we've deteriorated quality. So this is source 3, mean off target. If you recall, source 1 is normal variation from the mean, very normal. Individuals or averages will be normally distributed about the mean. Source 2 is instability of the mean. The mean is moving back and forth, up and down, without particular control. And source 2b is instability of the standard deviation. So when we go back to thinking about our control charts, source 2a is indicated by the average chart, and source 2b will be indicated by the standard deviation. Here in source 3, the mean is actually being operated off target. So off-target variability occurs whenever the actual mean does not coincide with the expected mean. So off-target variability is not always bad. In some cases, a shift in the process can represent an improvement. So take a look at the little graph on the right-hand side. Let's just say our target is where that arrow is, and the shift up is an indication that the mean has moved. Again, that might be good. For example, it might indicate that we've had improved performance, better miles per gallon. Let's hypothetically say that you are graphing the results of your 401k. Well, you'd be very happy to see it shift up, right? So not always bad. It just proves that it's different. So when is off-target variability a problem? Well, in production processes, off-target situations become problems when the deviation exists between the expected mean and the actual mean, which clearly will affect process capability. Expected versus actual, we'll get to that next. So what is the expected mean? Well, think about yourself as a consumer. You've gone to the grocery store and you go into the cooler and you buy your gallon of milk. While individual fills, let's say that gallon of milk may vary, on average, we would expect that weight of that fill to be, of that gallon, to be 128 ounces. With a MAV, that's a minimum accepted volume, of 125 ounces. You know, something can't be perfect. You know there's going to be some variation around the target, and you know that perhaps sometimes your fill is going to be slightly larger. But if you're a producer, falling below the expectations on a regular basis may result in penalties from government regulators. That would be an economic situation where you'd be cheating your customers. So that's certainly, that deviation from expected would be bad. In business, your president of your company has set an annual budget, let's just say, for materials as a percent of sales. So they set together their annual plan, and we know on average materials are going to be about 70% of sales, fixed costs are going to be X percent of sales, which leaves all other variable costs and profit to be squeezed out with a little bit left over. While individual spending on materials as a percent of sales may vary in individual months, falling continually above the expectation will deteriorate profit margin and the ability for the company to survive. So we may wish to move in terms of an improvement situation. We may wish to move towards the target. For example, if you are in operations and you are in charge of the maintenance department, you know that you're spending close to $100,000 a month on maintenance supplies 2 years ago. Well, that's an awful lot of money. Well, great news by selecting different vendors or making some very, very smart moves in terms of buying maybe fewer products or from different suppliers. Last year, you made a reduction and you only spent $80,000 a month. Well, that's like almost a $20,000 per month improvement. Well, your boss may say, gee whiz, we'd like to move that even further to reduce it to $75,000 a month. So that's an objective that you could graph on your average chart, as you can see on the right-hand side. Maintenance supplies and materials, you're trying to make the process go out of control in a good way. So fixing off-target variability is often associated with a change in the process variables that affect the process, such as, and those process outputs are weight and temperature, chemical composition, spending, like we just talked about, dimensions, performance, safety, and all the rest. We want to shift the process in some way to make things better. So off target of the mean involves shifting of the center of the distribution. That's, again, measured by and visualized by the average chart. And you see that on the right. Improving off-target standard deviation involves narrowing of the variability. And you can see that that is being portrayed on the range chart. So shifting of the center of the mean is affected and is measured by the average chart. And improving variability, the standard deviation, is affected or is indicated by the range chart. So we want to be able to know and have statistical proof of when these changes occur. And so when someone says, can you prove it? I'm going to give you 3 rules to prove that out of control conditions exist. Whether these rules can apply to bringing the processes under control or to prove that you've improved the process. So in terms of our discussion about managing the mean and the variability, I want to bring you back to this slide that you saw before on the horizontal out of control statistical analysis, sort of vertical in spec and out of spec. We're really talking about the realm of being in control and out of control, not at this point in time about capability analysis being in spec and out of spec. So 3 rules to identify control chart conditions on a control chart. Rule 1. First one, and this one is fairly intuitive. Maybe this is the only one you've learned, but whenever you see points beyond the control limit, that is a very, very good indication that the process has changed and somehow you need to address it. You've got to investigate why. You have to stop the process and understand why that point went out of control, because that's not normal. Rule 1, points beyond the control limit. Rule 2 are shifts and trends, and we'll call this the 7 points in a row rule. For example, on the right-hand side of the top of the chart, you see a shift in the process. The process was running somewhere between 15 and 20, very, very happy, and somehow now it's running between 25 and 30. And you can prove that you have this shift by counting the number of points. And typically we use 7 points in a row on one side to indicate a shift. It's indicated by one side of the average or the other, but it might be that it's running on average and it's shifted up or shifted down. Again, keep in mind that you're looking for something that looks significantly different. In this case, the average has shifted to clearly make the parts larger. Trends are defined as 7 points in a row that either ascend or descend. Now, what things could cause a product or a process output to ascend or descend? Well, perhaps temperature, perhaps you're running a machine that has some kind of tooling wear, and the tool is slowly changing and deteriorating one way or another, or sometime maybe a mold or a die is wearing out, and this may take a very long time. Point is, it's a trend that goes up or down, 7 points in a row that either ascend or descend. That's a trend. So of our 3 rules of identification of out of control condition, this is rule 3. You recall rule 1 is points beyond a control limit. Rule 2 is shifts and trends, and this rule is called non-randomness, or sometimes called stratification. Recall from our SPC clinic that in a normal distribution, you'd expect to see 68%, or roughly 2/3 of the points, plus or minus 1 standard deviation of the mean when you're talking about control charts, or plus or minus 1 standard deviation of the mean when you're talking about a distribution of individuals. So therefore, you'd expect to see the other 2/3 of the points within the other third of the chart. In the top chart, you can see that almost all of the points are within the middle third of the chart, which is kind of unusual. You'd expect to see points near the control limits as very naturally. In the middle chart, you see the same thing. Almost all of the points are near the control limits, and very few points are in the middle third. Again, that's non-randomness. You wouldn't expect to see that unless there's something wrong going on in the process. And of course, in the third chart, there's almost no variation going on, and really that's probably more of a measurement error problem that we're going to be talking about in just a little while. Rule 3, non-randomness. Control charts provide a look at within-group variation and use that within-group variation to use it to set limits on between-group variation. Let me tell you what I mean by that. If you recall from the SPC module, we calculated the upper and lower control limits of our average chart by using the measure of central tendency, that's the X double bar or the grand average, and adding to it something called the A2 times the average range, or the R bar. The A2, if you recall, came from a table, but the average range was a calculation of, again, the range within each subgroup is within group variation, and then we average those ranges to come up with an average range. So it was X double bar plus A2R bar became the upper control limit, and the X double bar minus A2R bar became the lower control limit. If the between group variation is within limit, that is, the points are within the control limits, it's all considered common cause variation. On the other hand, if the between group variation is not within the limits, like we see, or some kind of irregular pattern like we see in the lower chart, it signals an instability in the process that must be addressed because the process is clearly out of control. So like many statistical techniques, the control chart works by collecting data in groups. Once those groups are arranged, we can look at two different types of data, two types of variation, within group variation and between group variation. This is very important for you to understand this point in setting up the control chart. So if you I've got the little chart here on the right hand side, and it is sort of an explosion of that control chart that we were talking about in the SPC module. You can see that different times, 7, 7 to 15, 7:30, and so forth, we're collecting data, sample 1, 2, 3, 4, 5. So that's what we call a subgroup. So sampling production objects in consecutive order is the most commonly used method to capture within group variation. You're selecting parts that are as close to each other as possible, and you want that selection to be then recorded in that subgroup. Assuming that process is stable, the small differences in measured variation between consecutive parts is called inherent variation. So the within group variation indicates the variation that is exhibited within the subgroup. This within the subgroup variation, if the process is in control, is the best the process can produce given the current setup. Now, between group variation is the variation that we see from time to time from selection of subgroups. So again, indicating the arrow, it's the variation that we see between subgroups. So when we group data in production order, the between group variation represents a combination of any changes of shifts in the process or sampling error. So if the process is in control, we'll call that common cause variation. If the process is out of control, we're going to be talking about this assignable or special cause variation. So in the previous slide, we talked about within groups variation. In this slide, we're talking about between group variation. We're going to be talking a bit about this in the next few minutes. So we talked about a minute ago special cause and common cause variation. So special cause variation, this is variation that enters the process due to some special reason. It says here one, perhaps two, but typically there's one reason. It's observed as an out of control condition, and we must be paying great attention to this. It can often be measured and controlled by operators and may be easy to change. And we want statistical process control to be used and indicated by operators because it's real time. It makes no sense for us to collect data and examine it over the next shift or a week later. You lose the opportunity to make a change in improving the process when you don't observe the data and take action right when it occurs. So special cause variation indicates that something has changed. Common cause variation is the variation that's left over when the process is running in a stable manner. It requires a process change to improve if we want to improve common cause variation, and we'll get to that a little bit later. Common cause variation is typically much more difficult to improve. It's often management's responsibility because it typically costs money. But the emphasis here is we must pay attention to special cause variation. So two types of causes, special cause, often easy to pinpoint with SPC. Remember, I've given you those 3 rules. Usually has a short-term impact on the process unless it's left to continue. And machine line operators can typically diagnose those situations because they know really what's going on. Common cause variation, on the other hand, is not so easy to identify, requires more work in terms of practical problem solving to identify and improve, might require statistical techniques such as designed experiments to improve the process. And again, management typically needs to be involved in this to form a team and improve the process because they're going to be spending money. Special cause variation should be addressed immediately. Common cause variation is typically addressed harder and more by management. Well, another way to talk about common and special cause variation is shown on the chart. So you have what you see there is upper lower control limits, just say for X bar and R chart or an average and range chart, and see one point beyond the control limits. Well, that illustrates that that process has changed significantly enough that we need to stop and analyze it. We need to understand which factors contributed to that variation and which are possible to detect and identify. Those out of control conditions are evidence. They are evidence that some kind of disturbance was present in the data and it's affecting the process. So it's time to stop, understand it, and correct the process. So special cause variation is something that you need to investigate and repair in the process right away. They may represent large shifts in the process, like you see in the graph. On the left, you can see a tight distribution, then run significantly lower, then significantly higher, then right down again. So there's something really going on in this process that's causing the data to tell you that the product is changing significantly. These shifts could be in the mean or the center of the distribution, or it could be in the variability of the process. These shifts may be unpredictable and would be categorized as signs of instability in the process. So causes. So attacking special cause variation. If the process is not stable, it's not predictable. So if you have a process that's out of control and someone needs to ask you or you want to make an assessment of capability, it's really, really impossible to do that because it's sort of trying to assess something that's moving all around. It's really impossible to say what the process is capable of. Improvements are difficult to implement because we are trying to hit a moving target. Eliminating assignable causes is therefore a necessary first step in process improvement. That's why we talk an awful lot about control chart analysis, and identifying and correcting special causes. So in most cases, the control chart will be the only tool necessary for identifying and eliminating assignable causes of variation. Assignable causes are identified as out of control point, back to the three ways to identify out of control conditions. Because the source of variation is intermittent on the process, it's often easy to identify. The general approach is considered to correlate process variables to product characteristics. So you must go back into the process, understand the process controls, and understand why that point or those points went out of control. So on the right-hand side, I just listed some, if you were running a plastic injection molding business, some dimensional characteristics and variables that may impact molding dimensional characteristics. For example, mold temperature, mold conditions, screw speed, and so forth. So if you were seeing an out of control conditions in a plastic injection molding process, then you might be looking at these process variables when you stop the process to find out which one has gone awry. So we've been talking about special cause variation, but how about attacking common cause variation? So holy cow, Mike, you've been telling me it's so hard to control a process. We put our process in control. We've chased down all of our special causes, our assignable causes. Isn't that good enough? Well, it may not be. You may want to improve the process. You may want to go after all that variation that's left over, all that stuff we call now common cause variation. So Davis Boothie, in his book Reducing Process Variation, suggests that the most effective way to attack common cause variation is to break it down into components. He identifies 5 basic components which occur in the manufacturing process. So the basic strategy for dealing with the different sources is something we'll call as divide and conquer. So the types of common cause variation, I think, are very interesting. And you need to think about that. We're going to have some examples in the next few minutes to talk about this, and I'd like you to consider this slide about types of common cause variation. First is positional variation. That's within piece, examining a single piece. Is that single piece uniform in its variation? Let's say you have a machine part, a shaft, and you're measuring, and you're very interested in producing these in high volume off of, let's say, an automated lathe. But let's just take a look at the first part. Is that individual piece that you've run, is that completely round as it should be? Or is there variation towards one end of it or the other? So examine positional variation within piece variation. Second is part to part or between piece variation. So if you're measuring, again, this part that's coming off this automated lathe, so you measured the first part, and that's great. Now you went to the 100th part. Is the variation in the 100th part bigger, smaller, or the same as the first part? We'll call that part-to-part variation. Let's say you are running this screw machine process, and you run out of one stock of steel or aluminum or whatever you're machining, and you go to another batch or heat of steel, and you measure that variation. Does that batch or change of heat affect the variability? Is there more variation or less variation in the second or third heat or batch of steel? Batch to batch variation. Perhaps you're breaking your process down into multiple streams. For example, let's go back to the screw machine process, and you have the same raw materials coming into 4 different screw machines, 4 different lathes. Do you see difference in variability between lathe 1 or screw machine 1, 2, or 3, or 4? Stream to stream variation. And the fifth element of variability may come in terms of measurement error or gauge reproducibility and repeatability. Positional variation within piece variation, part-to-part variation between piece variation, batch-to-batch or heat-to-heat variability, process stream to process stream variability, and measurement error variability. We'll talk about each one of those as we go along. So Boothie, in his book, Reducing Process Variation, summarizes total variation in this way, sort of like an organizational chart. You have total variation, and you have special causes, and then common causes. And we've talked about how to attack the special causes, looking at shifts and trends, digging into the process, points out of control limits, non-randomness, and so forth, digging into those process variables and finding out what went wrong, and then examining common cause variation. And we just talked about measurement error, stream to stream, batch to batch, part to part, and within piece or positional variability. So recall what we said, common cause variation exists when there's no evidence of unnaturalness over a long series of points. Now, you can see that there is about the 3rd or 4th point there. There's a point beyond a control limit. Let's say we've addressed that. And then from that point on, the distribution of, in this case, averages illustrated by the average chart there, indicating a pretty good randomness. We'd say that process is in control. Patterns are stable. There's no sudden shifts or trends. Seems like the system of causes appear to be in balance and are in control. That's great. But we'd like to improve this. So very often we find that problems are not necessarily a result of out-of-control processes, but rather are caused by the normal process variation, common cause variation. In our SPC training, we learned that common cause variation accounts for perhaps 85% of total variation in the process. And this is perfectly normal. So we want to go after this 85% to improve process capability. So why should we be interested in attacking common cause variability? I mean, the processes are in control. Why even bother with it? Well, it's possible that the process may be in control, but the process may not meet the product may not meet specification, right? When we want to improve it, we may need to improve the downstream quality by reducing variability, and we may be able to, by reducing common cause variation, we may be able to reduce costs by using different materials or different methods. So some really good reasons for attacking common cause. While common cause variation is relatively easy to quantify, it's probably the most difficult of the three sources to correct. The sources of common cause variation are usually more difficult to identify because they're inherent in the process. For example, let's just say you are graphing the time it takes you to get to work every day. From the time you leave your house to the time you pull in the parking lot, you know there's going to be variability. And unless you've run into some kind of problem with a flat tire or something different, like you maybe run into a train or something like that, you know there's going to be some variability every day. But let's just say that variability we'll call it inherent in the process. But no matter what, whether it's in control or not, let's just say it's in control, you're to late work every day, so you're out of specification. So we must improve the process somehow so that we can, even though the process variability is good, we've got to improve the process. And that may take identifying, how fast you go or the number of turns you take or whatever is in your process that is making that process variability result in a product, and that is the time it takes you to get from home to work, excessive. So before we go on, remember we talked about the 5 types of common cause variation. Positional variation, that's within piece. Part-to-part variability, that's between pieces. Batch-to-batch variation. Process stream to process stream variation, and measurement error. In some situations, the very first thing, positional variation, wouldn't have any meaning. For example, if you have a swimming pool or if you're familiar with any chemical processes, how many samples do you take out of that bath of chemicals or your swimming pool if you assume that it's fully mixed? You wouldn't take a sample of 5, you just take a sample of 1 because positional variation doesn't make any sense. You wouldn't go to take a sample of chlorine on one side of your swimming pool, go on the other side of the swimming pool, and expect to see a different result. If our problem deals with non-manufacturing processes, for example, a business process, the categories of variation may have different meanings or may not exist at all. So you need to think about your particular business and how the variability is expressed. So now that we've established that positional variation may not have much meaning with some processes, and it's quite limited, we want to have a couple of exercises here and examples to talk about the other part-to-part variability, batch-to-batch variability, process stream to process stream variability, and measurement error. So I went on the internet and found this process that's filling bottles of beer. New Age Media has offered this on the internet. So if you'd like to go and take a look at this link, you'll see this process of filling beer, and then we'll discuss the variability, the potentials for variability once you've gone through that video. Well, now that you've gone through the video, you see that there's bottles flying everywhere being filled by different fillers and foaming beer all over the place. But I'd like you to think about naming the source of variability. In the top picture, it's bottles being filled by this enormous filler with many, many different heads. And would that be part-to-part variability if you're trying to measure a consistency of fill weight? It would be if each one of those heads are slightly different, maybe there's one or two or more of those heads that have some bad seals and giving a light fill, or also would be bad if somehow overfilling the bottle, that would be bad for the business. In the bottom picture, there's a photograph of bottles coming out and being put into cases by this automatic case loading process. So you might consider that batch to batch variability. So the picture on the top shows that enormous filler filling up bottles, each head having some kind of different characteristic of filling. So that might, again, you might consider that part-to-part variability. I don't think that would have much to do with perhaps batch-to-batch variability, unless you considered the product coming out of that huge filler one day to the next or 1 week to the next. That might be considered batch-to-batch variation. The bottom picture, I think, indicates some kind of gauging method that was somehow check weighing the weight of each, and that might be considered a source of variability called measurement error. Point is that we have 5 types of common cause variability. When you're looking at a process, you need to be thinking about how you can segment that those processes and what makes sense to attack in terms of common cause variation. Well, here's another example, and you know that food comes in canned products, shelf-stable products. Very normal for you to see them on the store shelves. They're great. These cans are filled at an enormous rate, hundreds and thousands of cans per minute. So the question is, how do we separate the sources of variation in filled weight in cans of food? Let's take a dive into the process. So in the food manufacturing business, to go into these little cans, the first bit of process is to prepare the ingredients in batch quantities. So if it's a chicken product or a seafood product or a vegetable product, all these products are going to be made and mixed in batches, and there's going to be some kind of inherent variability in the composition of each batch, because perhaps you can't exactly weigh all the ingredients in a very, very precise manner. So there's going to be some variability. The next thing that you'll be doing is blending those ingredients in some kind of a mixer or blender. That's shown on the right-hand side. If you look very, very closely, you can see the blades of the blender. Think of it at a huge, big mixing machine. And then you can see the output of the product on the left in this big batch. And it's thousands of pounds of material, and you say, gee whiz, it should be homogeneous, but you know that it's going to have some kind of variability. The question is how much. In this step, we blend and mix and then pump and perhaps test it as it goes to the next process. And then you're going to fill the cans in this filler. This filler is much smaller than that example that we showed with the beer production. It's going to be putting the food into the cans and then applying a lid and seaming and closing those lids so they go on to the next process. So the filling process, by just inherently, because each individual filler head is going to be different, and its ability to fill exactly the same. You might consider variability within each filler head. This positional variation. Does each filler head, let's just say filler head 15, does that fill consistently or not? And certainly there's going to be variability part to part between heads. And once you get them filled, then they're washed and then they're date coded, and then they go on to the sterilizer. That's the magic of shelf-stable products, that they can be produced and put on a shelf for a very, very long time and still be good, because in the sterilization process, you've killed all those pathogens, if there were any. And then finally, it goes into the shipping room, or goes on to the next process to be packaged with something else, or goes right out to the consumer we'll call that test, label, and pack. And when you're drawing products from that, certainly you're drawing, depending on where you are in the stream, are you in the producer's warehouse, or are you at the customer's large warehouse, or is it in the distribution chain at the large grocery stores, or where, depending on where you are in the process, you might consider batch-to-batch variability. So in this case, we're interested in measuring fill weight, and so I've come up with a procedure as if you were to measure the fill weight, and that's important. That's maybe the characteristic that we're trying to measure. So you're going to select at random one can and one lid from the materials inventory being used for production. So we're not interested in so much in the weight of the can and the lid, we're interested in the weight of the food. So you tear it out on the gauge, on the scale, and go from there and set it at 0. Then you're going to weigh cans. You're going to select 10 cans at random from the process while it's operating, and you're going to record the weight, give yourself an average weight, and also be able to measure the variability of that sample, and you record it on some kind of document, perhaps record it in your SPC, statistical process control record software. So now we're talking about examining that common cause variability. Let's just say all the special causes have been addressed, everything's running fine, all the batches are well mixed, and everything's great. All the filler heads are running as they can. They're running very, very well, or the best they can. But we're intending to improve the process, reduce the variability, and make it even better. So we go to our 5 points of common cause variation. And trying to think about what could we do to improve variability. Well, we maintain integrity of our measurements for positional variability by weighing one can from each of the heads. That way we can detect if there's any variability between heads. And certainly another way to look at integrity of positional variability is to measure a series of cans from a single head over and over and over again, to see how much variability we have inherent in one particular head. We lose positional variability by selecting cans at random. So by tracking the cans and understand how those can fills are associated with each one of the filling heads is a way for us to track down positional variability. So if we back up in the process, we want to measure variability within and between batches. Well, we can learn about within batch variation. We can measure the filled weight of the can at the start, middle of each batch. Is it possible that that batch was not well mixed, or somehow did it settle from the time it was produced? Let's just say it takes 15 minutes to run a batch. I don't know. But do the cans somehow weigh differently at the beginning, middle, or end of the batch? They shouldn't if that process is fully mixed and homogeneous. But it's important for you to understand that and relate that to the batch. Or is there a variability between batches? So let's just say you select samples from, if you're going to make 50 batches in a day, you select samples from batch 2, select batches from batch 20, and select batches from batch 49. And is the difference in can weight significantly different between batches? So that's our third common cause of variability, batch-to-batch variation. I'm asking you to think about how we could sort of deconstruct the variability in our process to understand how to improve common cause variation. So what variation would we consider if you wanted to significantly attack common cause variability? Well, if you sample cans selected from retains of filled cans, you can produce by one filler and one batch. That's pretty basic. One filler over 6 consecutive batches. That would tell you something about batch-to-batch variation. Multiple fillers and one product in one shift. Well, maybe you have multiple filling machines and you want to be able to detect variability between filler 1 and filler 2. Is there a difference there? Most likely there is. How about one filler and 10 different recipes over the course of the month? Well, you have, let's say product X, which may be a vegetable going in a can, and maybe that vegetable has different ingredients or different sizes than the next vegetable. Does that impact the fill weight? Well, maybe it does, and maybe you need to understand that. If you assume that it's the same, maybe you're right or maybe you're wrong, but one filler and 10 different recipes over the course of a month, or multiple fillers and multiple products over a 6-month period. Point is, you're trying to extract the variability by examining those 5 common causes of variation. What about measurement error? You assume the gauge is great, but how do you know for sure? Well, there's a study called MSA, or Measurement System Analysis, which assesses the adequacy of measurement systems for a given application. Measurement systems analysis answers questions such as, how well does the measurement system describe the difference between the observed measurement and the actual measurement? Is the observed measurement the true measurement? Can the measurement system adequately determine the difference between different parts? Let's go back to the idea of the lathe, for example. If you're cutting parts that have 1 inch in diameter and using a caliper or a micrometer, and you change the setup, and now you're making a diameter of 1.5 inches or 2 inches, can that same gauge adequately measure with very little error both parts, a 1-inch part and a 2-inch part? Does that measurement system stay stable over time, or does it change? You see this often with machine parts where people will leave their gauges on the machine at the beginning of the shift. That gauge or the micrometer or the vernier is cold. Over time, as the machine warms up, the gauge also changes because of it warms up too, and that might impact the gauging accuracy or variability, or as we're going to talk about, linearity, or it might be just something to do with age or wear of the gauge. Does the measurement system, is it accurate throughout the range of the part? For example, if you're using a vernier caliper that has a capability of measuring from 0 to 4 inches, is it just as repeatable and accurate between 0 and 1 inch as it is between 3 and 4 inches? It might be different. And can different operators achieve the same range of measurements on the same part? So if you put up your operators, operator A, B, and C, and you give them standard parts and to measure those parts in exactly the same way, exactly in the same place, do they come up with the same measurement? So that's something that's what we call a study of measurement analysis, MSA, measurement systems analysis. We'll talk about that. When we're talking about measurement error, we want to introduce this concept of accuracy versus inaccuracy, precision versus imprecision. First, let's talk about accuracy. In the upper left-hand quadrant, you see if you will use the analogy of a target, the bullets or the arrows hitting the target pretty much dead in the center. We'd call that accurate and precise. It's on target and the points are very close to each other. As opposed to, on the right-hand side, it would be precise but not accurate. Somehow, if we could focus that tight group to the left, it would be accurate and precise. The lower left-hand quadrant, certainly that's not precise. That's accurate, which it's pretty much in the middle of the target, but it's simply not precise. And worst case situation, you could be inaccurate and imprecise. So thinking more about measurement error, we're going to introduce some terms. Resolution is one. That resolution is the ability of a measurement system to discriminate between measurement values. And we see this error being introduced oftentimes when you're looking at a control chart and you see all the points on a control chart that are very, very jagged, or they're extremely linear. there's very little deviation in the measurement in the control chart. You say, gee whiz, why is that? Well, it's because the precision that you're trying to obtain is certainly not, the resolution you're trying to obtain is certainly not available in the gauge. So the rule of thumb when you're setting up a control chart is that the measurement system should have a minimum of 10 measurement increments within the product tolerance. For example, if you're measuring something that has a plus or minus a half an inch variability, tolerance plus or minus a half an inch, the minimum resolution should be a tenth of an inch. So the width of the specification is 1 inch. The minimum measurement, the minimum increment of measure should be a tenth of an inch. So examine your gauges to make sure that you've got this resolution issue licked. Measurement error, let's go back to the bullseye. Accuracy is the difference, it's the distance between the average value of the measurements and the true measurement. So in this graph, you can see that you're going to get a distribution of measured values. And if the distribution represented by the curved line, the distribution there, is off of the true value, we could say it's inaccurate by that amount. So think about accuracy as a distance or amount of measurement that's off of the true value. Another thing that we want to talk about is something called linearity, and that's the consistency of accuracy or bias over the range of measurement. So let's think about the red line, and that is on the horizontal axis, you have the true value going from, let's just 0 to a number 100, and on the vertical axis, the measured value. And what you want to have is perfect linearity, that is, no difference between the true value as it gets bigger and bigger and bigger, between the true value and the measured value. Think of it as that red line. Well, perfect linearity, but with a constant bias or a constant error, is represented by the yellow line. It has a very, very good linearity. It's just that it starts at a different point. It's the starting point is off. And poor linearity is one where the gauge changes and gets worse one way or another in terms of being able to measure. It's, in this case, has more error, more bias as the part gets larger and larger and larger. So that's the issue of linearity. Another element of measurement error has to do with operators. And we're going to be talking about repeatability in this slide, and the next slide, reproducibility. Repeatability is the consistency of a single appraiser to measure the same part multiple times with the same measurement system. So let's just say you start out with a part and you know exactly, you mark the part, you know exactly what the dimension is. You've taken it to your calibration lab and you got the experts there and they tell you it measured exactly X. And you give this operator this part, not necessarily ask them to measure it 10 times in a row. You may ask them to measure it 10 days in a row. Don't tell them that it's the same part. And you see, will that same operator measure that same part and give you the same dimension? That's repeatability, an assessment of operator gauging error. So in the previous slide, we talked about repeatability. Now we're going to be talking about reproducibility. And that's the consistency of different appraisers in measuring the same part with the same measurement system. So in this case, appraiser 1, 2, 3, 4, and 5. They again have the same part, been instructed to measure it in the same place over time, different times. Do they give you the same result? And if all those curves would overlap, that would be great. If not, that difference in distributions of measurements is called error of reproducibility. So when we're talking about accuracy and precision, precision on the top, accuracy displayed on the bottom. Accuracy is typically easier to deal with because you can usually calibrate a gauge if that's the problem. You can bring it back to zero, bring it back to a set point. Maybe the gauge has been dropped, misadjusted, something. You can set it and it'll be great. On the other hand, precision is more difficult to handle because there may be something to do with the gauge wear that is causing you to have an imprecise measurement. So altogether, correcting for accuracy, measurement error is a statistical summing of the error generated by repeatability and reproducibility. If you can move accuracy and zero it out, reproducibility and repeatability are the issue that we're talking about overall in terms of measurement error. So there are books that are available to guide you through this issue of measurement error. One that I would point you to is through the AIAG, and they have a great book on measurement systems analysis. And they provide you formats. Also, there's a number of statistical programs, software programs that will guide you through this issue of measurement error to automate the process. So I want to thank you for your attention during this session. Please proceed to part 3 of understanding variation to solve problems. But before you go, just take a look at the references and credits so that if you're interested in understanding more deeply the things I've talked about in this module, please do. Thank you very much.